Good morning. Welcome to DEF CON. Today I will talk about a topic, macOS and iOS kernel debugging and Heap Feng Shui. So here is the outline. First, I will introduce myself and what is the kernel. Then I will introduce how to do kernel debugging on macOS and then iOS. Then I will use these debugging techniques to debug a real kernel heap overflow. Last but not least, I will introduce two methods to do Heap Feng Shui. Okay, let's start. So who am I? My name is Min Zheng. You can call me Spark. I'm a security expert at Alibaba, and I'm a PhD in COHK, and I'm a member of Blue Lotus and Insight Labs. I worked in FireEye, Baidu, and Tencent before. Our team have achieved a private jailbreak in iOS 9, and we will show more details in the future. Here is my Weibo and Twitter. You can follow me and ask me questions on that. This work has a co-author called Liu Xiangyu. He is my colleague and he is a security engineer at Alibaba. I also want special thanks to my friends which helped me in this work. The topic is kernel debugging. What is the kernel? The kernel is actually the XNU. XNU is the computer system operating system kernel developed by Apple. It is open source software as part of the Darwin operating system. It has an abbreviation called X is not Unix. We know that XNU for macOS is open source. It can be compiled and debugged. However, XNU for iOS is not open source. You cannot compile it or debug it officially, but most implementations is the same as macOS. However, we can use some tricks to do kernel debugging for iOS too, and I will introduce it later. Let's talk about macOS debugging first. A wise man once said, to do a good job, one man must sharpen one's tool. So we need to buy some equipment. First, we need 2 MacBooks or 1 MacBook with virtual machine. The system version can be different, which means you can debug iOS 10.10 on iOS 10.11. Also, you need to buy some converters or keyboards like Thunderbolt to FireWire or FireWire keyboard. After we have the equipment, we need to install KDK on the 2 MacBooks. For the host MacBook, we need to execute a command called fwkdp. For the debug MacBook, we need to copy the kernel.development of KDK to the system library kernel folder in the debug MacBook and execute the following command. This command will set the environment and reboot the debug MacBook. After rebooting, the host MacBook can start debugging with commander lldb kdp remote localhost. Note that we can get kernel slides immediately. It is very useful for us to debug the kernel. Also, we can use some command like image list to get the kernel address of partial kernel extensions. Note, we can only get partial kernel extensions. If we want to get all the kernel extensions, we need some other ways. Just like JDB, we can use x/nx to read the data in the kernel. Also, we have 3 ways to set the breakpoints in the kernel. We can use b asterisk address to set a breakpoint in the LLDB. We need to use the offset of the kernel cache plus the kernel slice to calculate the address. Another way to pause the debugging machine is to use a shortcut key. You can use command plus alt plus control plus shift plus ESC all at once, and it will pause the debug machine immediately. We can also set breakpoints in the XNU source code through int $3 and print kernel information through printf. Note that if you use this way to debug the kernel, you need to recompile the kernel and then put it in the debug machine. Also, we can use command script import this command to load the Python script in the kernel, in the LLDB. It is very useful because this script can help me get a lot of information about the kernel. For example, you can use the print to print the zone information, and you can use show the free list to show the element information in the free list. There is another command called show all kernel extensions. This commander can get all the kernel addresses of the kernel extension. In addition, you can implement your own Python script. You can find some examples in the KDK's Python folder. Okay, so let's talk about iOS kernel debugging. We know that there is no official tools for iOS kernel debugging, but we can use some tricks to do that. Before we debug the iOS kernel, we need to get the kernel cache. Unlike macOS, we need to decrypt the kernel cache. Before iOS 10, the kernel cache was encrypted. You can find the keys in the iPhone wiki website and then decrypt the kernel cache. After iOS 10, there is no encryption, but there are some encode, so we need to unzip the kernel and decode the kernel using image 4 tool. After that, you can extract kernel information through Joker and Ada. Note that there's no breakpoint in iOS, so the most common way to get the register value is to use the panic log. Something should pay attention is if there are too many panic logs in your phone, the system will stop generating the panic log. So if you want to debug your iOS system, you need to delete the panic logs if there are too many. So you can use these two methods to do that. One is for jailbreaked iOS, another is for unjailbreaked iOS. Although there's no KDK in iOS, we can still use kernel task port to do arbitrary kernel memory read and write through two userland API. One is called macvm read, another is macvm write. But what if we don't have the task for PID patch or no jailbreak? What should we do? Well, you first need a kernel vulnerability. Then you can use this vulnerability to get the kernel task port. Then you can restore the kernel task port into the host special port. Then you can use a userland API called host get special port to get the kernel task port in the userland, and then you can use macvm read and macvm write to do the kernel read and write in the userland. After getting the kernel task, the next step is to figure out the kernel text base and slide. In ARM32, it's easy because there's only 256 potential locations for the kernel slide. But in ARM64, it's not easy. We need to do something like first create an OS object in kernel. Then we need to find its vtable pointer, which points to the kernel's base region. Then we search backwards from the vtable address until we find the kernel header. The source code can be referred to the iOS kernel utilities project. After getting the kernel slide, we can get the root privilege for our applications through the kernel read and write. And then we can use offset plus kernel slide to find the kernel object address of related ports in memory. It is very useful to debug the MAC port in the XNU system. So now I will show how to use the debug techniques to debug a real kernel heap overflow. This vulnerability exists in the mark voucher extract attribute recipe trap. This is a new function added in iOS 10 and macOS 10.12. So that's why there's no jailbreak for iOS 9.3.5 because this function does not exist in that version. It's a new function in iOS 10. This mark trap can be called inside the sandbox, so we can attack the kernel inside the sandbox. This function will first use copy in to get the recipe size from the userland and save this size to the SZ. Then it will use keylog to allocate a SZ size a block of memory with this size. And then it will use copy in to copy the data from the userland to the kernel. However, the developer forgot that the recipe size was a user mode pointer, and then it used as a size value in the copy in. We know that a user mode pointer may be very large than the size value, so it may cause the heap overflow. If we want to debug this vulnerability, we can set the breakpoints before and after copy I/O. The address are calculated through the offset in the kernel cache plus the kernel slide. So as you can see, before heap overflow, we can find the flag of dead beef. The dead beef means this block of memory are unused, but the next block of memory is used with FFF. After we trigger the heap overflow, we can find the first block is full of our data with A, and then the next block of memory is overflowed by the first block of memory. It overflowed 32 bytes with character B. So now we have the ability to overflow arbitrary content of data, but we need to find a way to do the kernel read and write. So we need to do some Feng Shui. There are two ways to do Heap Feng Shui in iOS 10 and macOS 10.12. I will introduce the first one. We know that in iOS 10 and macOS 10.12, we cannot use the classic VM map copy techniques to do the heap Feng Shui by changing the VM map size, because Apple added a new mitigation that they will check the free into the wrong zone attack, which means if you change the size of the VM copy, the kernel will panic. So we need to find a way to avoid that. Luckily, Beer in Google Project Zero proposed a new way to do heap Feng Shui through the pre-alloc mark port. The basic idea is to use mark port alloc full to alloc IPC key message objects in the kernel memory. The object contains a size field. We can corrupt it, and it doesn't have any pointer, so we will not corrupt any pointer in the kernel memory, so it will not be panic. By using the exception port, we can send and receive the data in the kernel memory, and this data will not be freed. It's very important. And the data we used to send is the register value of the crash thread. So if we want to send the information to the kernel, we need to create a thread and set the register value we want to send, and then crash the thread. The data will be sent to the address of IPC key message objects plus IKM size minus 104. So why the number is 104? We can use kernel debugging to figure out it. First, we use kernel debugging to figure out the address of pre-alloc port buffer in the memory. Then we can trigger the exception and send the data to the kernel. After that, we can use kernel debugging machine like kernel read to get the data, to inspect the data of the buffer. As you can see, we can find the location of the data in the buffer is D3C because we set the value of the IKM size to E40. Therefore, we can get 104 at last. So that's why the number is 104. So now we get the object to do the heap Feng Shui. The next step is to rearrange the kernel memory. First, we allocate 2,000 pre-allocate ports to ensure the following ports are continuously. And then the attacker can allocate 3 ports. One is the holder, the second is first port, the third is second port. Both of them are in the zone 4096. Then the attacker can free the holder and use the overflow, the vulnerability to overflow the first port. The overflow data contains the IKM size and other fields of the IKM object. The key point is to set the IKM size to 1104. So why is 1104? We can do a simple calculation that the address of the first port plus 1104 minus 104, it will be the address of the second port, which means we can control the second port through the first port. So if we can control the data of the second port, the next step is to get the address of the second port, which means we need a heap information link. So how to do that? The first thing is the attacker use the first port to give the second port a valid header. If the second port has a valid header, you send the data to the second port. The second port's IKM next and IKM previous will be set to point to itself, which means if you receive the data from the kernel to get the data of the second port, you can figure out the location of the second port in the kernel memory. After getting the heap address, the next step is to get the kernel slide. But before we do that, we need to safely free the second port. The reason is if you don't do that, the system will be panic because the kernel detects some memory corruption. After freeing the second port, the attacker can allocate a user client to hold the spot of the second port. Then the attacker can get the user client object through the first port. Note that the first 8 bytes of the kernel user client object is the vtable address. So which means you can use the vtable address in the kernel cache compare with this dynamic vtable address. Then we can calculate the kernel slide. In this case, the kernel slide is 1BC00000. After that, the attacker can create a rope chain which can be used to do the arbitrary kernel memory read. He can use OS centralized with UUID copy. In this way, the attacker can copy the data from any address to the kernel buffer base plus 48. And then use the first port to get this data back to the user mode. If we reverse the X1 and the X0, he can get kernel memory write because one is to do the read, another is to do the write. So we get the rope chain. The next step is to trigger this rope chain. We can trigger this rope chain through the IO Connect get service. This method will invoke get mental class return and release method. So we can create a fake vtable and send it to the second pod. Then we can use IO connect get service to trigger the rope chain. We mentioned before to do the kernel read and write. When we get the ability of kernel read and write, we can do the kernel patch. The latest and public kernel patch technique could be referred to YALU. Note that this traditional Feng Shui is not stable because it needs to do multi times and use a lot of rope chain. It only have a 50% successful rate. So if we want to have a high successful rate, we need to use pod Feng Shui. So what is pod? We know that mark message is the most frequently used IPC mechanism in XNU, and we can use complicated message to send out of line ports to the kernel, which means we can send the ports object to the kernel. And in this case, we will send 32 mark port to the kernel, and each port use the 8 bytes, and 8 bytes multiply 32 is 256. So the data will be sent to the zone 256. Note that the out-of-line ports saved in mark message are the IPC object pointer, and the pointer can be pointed to the user mode address. Therefore, the attacker can overflow those pointers and modify the pointer to point to a user mode. And then we can control this port in user mode and also create fake tasks for this fake port as well. So how to overflow the right port? The right port is the key. So we need to do some Feng Shui to rearrange the kernel memory. The first thing we should do is to send lots of OOL port to the kernel to ensure the new allocated blocks are continuous. And then the attacker receives some message in the middle to dig some slot. Then the attacker sends some message again to make the overflow point at the middle of the slot. After that, the attacker can trigger the heap overflow vulnerability at the overflow point. Then we receive all the port from the kernel and check the value of the port. As we mentioned, we send the dead port to the kernel with FFFF. If the value changed to some other value, which means this port is overflowed by us, and we can control this port in userland. So if we can control a port in the kernel, we can use this port to do arbitrary kernel memory read. How to do that? We need to set the IO bytes of the fake IPC object to IKOT task and craft a fake task for the fake port. By setting the value at the fake task plus the process of, the attacker can do arbitrary memory read. It is amazing because the function doesn't check the validation of the task and just return the value on that address. As you can see in this function, it will use port name to task to get the fake task, and the fake task is controlled by us. Then it will use get BSD task info to get the information, and so the function will use A1 plus 380 to get the data on that address, and this address is controlled by us. Also, it will use the process PID to get the information on the A1 plus 10, and this address is also controlled by us. So we can get this. So we can get any address in the data in any address, and we get the kernel arbitrary read ability. Then we can dump the kernel IPC object and kernel task to our fake IPC object, and copy it to our fake IPC object and fake task. Then we can use a userland API called task get special port to get the kernel task port. Then we can use this kernel task port to do to call the two API. One is mark VM read, and one is mark VM write to do arbitrary kernel read and write. So here is the conclusion. We talked about kernel debugging. It is very useful for us to do kernel exploit development. And we introduced the two Heap Feng Shui techniques. One is traditional Heap Feng Shui because it needs rope chains to do kernel memory read and write, and it needs to do multi-times, so it's not stable. For port Feng Shui, it doesn't need any gadgets and only use this structure. It's stable with a high successful rate, but it's very easy for Apple to fix it. So that's all for my talk. Thank you for your listening. Do you have any questions? Sorry, I take a long time.